Okay, hi everybody. Today we are going to go through 5.1 notes about perpendiculars and bisectors. So, first of all, first definition here, we have a perpendicular bisector. This is a segment, ray, line, or plane that is perpendicular to a segment at its midpoint. So here's our perpendicular bisector. Remember, when we have something that's perpendicular, it creates a right angle. And a bisector will cut our segment in half. So it cuts this segment from A to B directly in half, giving us two congruent lengths. Next, we have a perpendicular bisector theorem. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So here, if CP, so here's CP, is the perpendicular bisector of AB, of this segment AB, then AC equals BC. So AC here will be congruent to BC. Now we have the converse of the perpendicular bisector theorem. If a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So here, if DA, so here's DA, is equal to DB, meaning these two are congruent, then D is on the perpendicular bisector of AB. So our point D here is on our bisector. Next, we have our angle bisector theorem. If a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. Here, if the measure of angle BAD, so this angle here, equals the measure of angle CAD, so this angle here, then DB, so this segment here, is congruent or equal to DC. So these two segments are congruent, so I'll mark those with two tick marks to show that they are congruent. Finally, we have converse of the angle bisector theorem. If a point is in the interior of an angle and is equidistant from the sides of the angle, then it lies on the bisector of the angle. So what this means is if DB equals DC, so this segment here is equal to this segment here, then we can conclude that the measure of BAD, so this angle, equals the measure of CAD, then this angle. Okay, now let's move on and do some examples. Example 1, in the diagram shown, MN is the perpendicular bisector of ST. So here's MN. It's our perpendicular bisector of ST. Remember, it creates a right angle. A says, what segment lengths in the diagram are equal? Well, since we know that we have a perpendicular bisector here, we can conclude that this segment here, N to T, it should be congruent to N to S. So let's write that down. Segment NT will be congruent to segment NS. We also have another two set of segments that can be congruent here. Our last two are going to be MT and MS. Since we have that perpendicular bisector and they meet at point M here, we can conclude that these two segments are congruent as well. So MT now will be congruent to MS. B says, explain why Q is on MN. Notice Q is over here, our point Q, but our segment that they drew here doesn't necessarily go through that, but we know that Q will be on this line because there's an arrow here, and this arrow is going to go all the way through. So this is why Q is on the line MN. We know that since QT is congruent to QS, so let's look at what that says. QT is this segment here, and it is congruent to QS. How do I know that they're congruent? Well, they both tell me that they're 12, that they have a length of 12, so I know that they're congruent. Since those two are congruent, we can assume the perpendicular bisector will go through point Q. And we are done there. For number two says find PQ. Notice PQ is the length here. We know that that length is 3x plus 1. Notice we have an x in there. We have a variable. So we're going to have to solve for a variable x here to find that length of PQ. Notice that the line SQ here, the dotted line that I'm highlighting now, that is a perpendicular bisector. I know that that is a perpendicular bisector because of this right angle here and these two congruent tick marks. It shows me that this segment is congruent to this segment. Since I know that that's a perpendicular bisector, I can conclude that PQ should be congruent to RQ. If two things are congruent, we can set them equal to each other. So I know that PQ is the length 3x plus 1, and it is congruent to RQ. RQ is the length 5x minus 3, so we can set those equal to each other since they are congruent. Now we have an equation where we can solve for x. So I'm going to subtract 3x and subtract 3x from both sides. That will cancel. I'm left with 1 equals 2x minus 3. If I add 3 and add 3, I'm left with 4 equals 2x. If I divide by 2 here, x will equal 2. That's not my answer though. Remember, we're trying to find the distance of PQ. Here I know that PQ is 3x plus 1. So I know that I'm going to have a 3 times x, but now I know that my x is 2 plus 1, and now I just simplify that. So that will give me 7, which is the distance of PQ. That is our answer. Let's move on to number 3. Find QS. So we're going to find the length of QS. Here's QS. I'm highlighting in red. Notice that I have a 4x minus 1 as that length again. So again, I have a variable x. I need to solve for that variable. Here, I notice that these two angles, angle QPS and angle SPR, are congruent. If those two angles are congruent, and I notice that I have two right angle boxes here, I can conclude that QS should be congruent to SR, that those two segments should be congruent. Again, when we have two congruent segments, we can set those equal to each other. So I'm going to have 4x minus 1 equals 3x plus 2, and I can solve here. If I subtract 3x, subtract 3x, I'm left with x minus 1 equals 2. Add 1, add 1. I get x equals 3. Now we just have to plug that x back in for my distance of QS. My QS distance is 4x minus 1 here, so I'm going to plug x in there. So 4 times x, which is 3, minus 1. If I simplify that, that will give me 11. So my distance from Q to S is 11. Now we have a theorem here, in-center theorem. The angle bisectors of a triangle. Let's pause right there. Remember, an angle bisector, a bisector cuts in half. So our angle bisector will cut our two angles in half. So the angle bisectors of a triangle intersect at a point called the incenter that is equidistant from the sides of the triangle. So here in our diagram, the incenter is this point P here right in the middle. For example, if P is the incenter, like I just said, then PD will equal PE will equal PF. So this distance will be 5. For example, this distance will be 5. And this distance will be 5. All of these segments will be congruent, so I'll mark them with 1 tick mark. That's the in-center theorem. Let's move on to number 4. Find SU if S is the in-center of triangle MNP. So here's my point S. I know that that is the in-center. I'm trying to find the length of SU, so this length here. That length is in this triangle that I'll outline now. So we're going to be thinking about this triangle that I'm outlining. If I redrew this triangle, it would look like this. I know that it's a right angle because of this right angle box. I know my hypotenuse is 10 from right here, and I know one of my legs is 8 from right here. I'm going to solve for this missing piece, which would be SU. So I'm trying to solve for SU. Here we're going to use the Pythagorean theorem. The Pythagorean theorem says a squared plus b squared equals c squared. In the Pythagorean theorem, a is a leg, b is a leg, B is a leg, and C is always the hypotenuse. So here, let's label on our triangle what we have. Let's label each piece. My 10 is my hypotenuse because it's the angle directly across from my right angle, or sorry, it's the side length that is directly across from my angle. So this is my hypotenuse. So this will be C. Here I have a leg, so that's going to be A. And here I have another leg as X, but that's going to be B. So I'm going to fill in those values in my Pythagorean theorem. So I know that A is 8, so that's going to be 8 squared. And my B here is X, so I'm going to say that that is X squared. Equals C squared, but C squared here is 10, so that'll be 10 squared. If I simplify this, I'm going to get X squared equals 36. Then I will do the square root of both to get rid of that square, and I'm going to be left with X equals the square root of 36. The square root of 36 is 6. So X will now become B, so B equals 6. So the distance of SU, this distance here, the distance of SU is 6. Finally, number 5, our last one. Find the measure of angle BCD. So let's look and see what that angle is. Here's B to C to D. So the angle that we're dealing with is, we're trying to find this missing angle here. If D is the incenter of triangle ACF, so I know that D, this point here in red, is the incenter of our entire big triangle here, the whole thing. So there are a few ways we can do this. First of all, I'm going to think of this triangle as a whole, the whole thing here. I'll highlight it all. We're going to think of it as one big triangle. I'm going to, since I know that D is the incenter, then that means that this angle will also be 35 degrees. Since D is the incenter, this angle will be 29 degrees. So now I have, if I think of it as one big triangle, I have two angles here. If I add these two miniature angles here, 35 plus 35, that'll give me 70 degrees. And that is the measure of angle A. So angle A equals 70 degrees. I'm going to do the same thing over here for angle F. Angle F, 29 plus 29, that will give me 58. So now I have two angles that I added together to get my one big angle here for each of these. Angle A is 70, angle F is 58. Now I just need to solve for this missing entire angle here, and then I can split it in two. So remember, this is our triangle sum theorem. The triangle sum theorem says that three interior angles of a triangle have to add to 180 degrees. So I'm going to go 180 minus the two angles that I know. I know that angle A is 70 and angle F is 58. If I do that math, I'm going to get 52 degrees. So the entirety of this angle C, so angle C is 52 degrees. But notice that angle C is cut in half here, and we're only trying to solve for this angle here. So if we cut angle C in half, all we have to do is divide by 2, and that will give us the measure of angle BCD. 52 divided by 2 will be 26 degrees. So this angle will be 26, this angle will be 26, and we are done.